Welcome to the organic chemistry section of our practice MCAT questions. In this video, we're going to be going through questions 101 to 105. So first, I'll show you guys a question so that you can pause the video and attempt them on your own. Here's question 101, 102, 103, 104, and 105. Now let's go through the question together. In question 101, we're asked which of the following functional groups is not contained in the given molecule. So 3 of these are, and the rest are not. So for this, you should be able to convert the names that you see into the actual representation of the functional group. A methyl, where is that? It's right here. A methyl group is a CH3 functional group that's attached somewhere else to the rest of the molecule. We see methyl right over there. Carboxyl, what does that look like? It's a carbonyl where the other group that we have on the side is an OH. It's a carboxylic acid. Do we have that? No, we do not. This carbonyl that we see over here, let's see, we see 2. This one on the left, that's a ketone. And then this other one on the right, that is also a ketone. Because if you look to the left and right of it, we have carbon here and a carbon here. You see an OH attached nearby, which might kind of make you make the mistake of thinking that it's a carboxylic acid, but no, if you look at what's directly attached, it's a carbon. So this is a ketone because it has 2 carbons on either side, but if it had an OH directly attached to it, that would make it a carboxylic acid or a carboxyl functional group. Because of that, we can say that this is the one that is not contained. So we were asked functional groups that are not contained. The carboxyl group is not contained. The methyl group is. The carbonyl, this is just a double bonded oxygen, and then we can see 2 of these. So carbonyl is present. So a carboxyl is a type of carbonyl, and a ketone is also a type of carbonyl, and we can see 2 ketones. So carbonyls are present, and option D is saying a hydroxyl group. That is also present. That's when we have this single bonded OH group, single bonded oxygen to a carbon. That's an hydroxyl group or an alcohol group, and that is also present in this molecule. So our correct answer is B. In question 102, it says ethene and ethyne differ in terms of their blank. So we're talking about ethene and ethyne, which means we are talking about a double bonded carbon and a double bonded molecule with 2 carbons, and then a triple bonded molecule. The Eth tells us that we have 2 carbons, and then ene and ine tell us how many bonds we have between them. So these are the 2 molecules that we're talking about. The main thing which differs is that additional bond in the ethyne. And now let's look at which properties we're discussing. Boiling point, is that something that differs? For these simple hydrocarbons, so without too many other things attached, we're just talking carbons and hydrogens, you should know that between the double bonded one and the triple bonded one, and then naturally between also single bonded and triple bond, there is a difference in terms of boiling point. It's not as strong of a difference, but there's a slight difference as well between single and double bonded as well. So boiling point is something which differs. Number 2 is saying the number of sigma bonds between the carbons, and then number 3 is saying the number of pi bonds between the carbons. So for this, you should keep in mind the hybridization of the bonds between these 2 atoms. When we have a single bond, we have an sp3 bond, which means that we have 1 sigma bond. So the sp3 bond, it uses the s orbital, and then it hybridizes 3 of the p orbitals to give us a sigma bond, which is that single bond between the 2 carbons. And then for the other ones, that first single bond, just remember, it is a sigma bond made from hybridized orbitals, but then afterwards we have some unhybridized p orbitals that are used to make additional bonds. So for the ethene, the double bonded one, we have an sp2 bond, and then down here we have an sp. So we have 1 sigma for both of them, but the difference now is for the double bonded one we have this additional bond. How is that made? We just took sp2 now instead of sp3, and we left one of the p orbitals on each of the atom unhybridized. That can be used to come together form another bond, which is that double bond, and that is called a pi bond. Similarly, in the case of the triple bonded one, the ethyne, we have 2 pi bonds. That's why we left 2 p orbitals unhybridized. So that's the main difference. They all have the same amount of sigma bonds to form that first bond, but the difference is the number of pi bonds. So 2 is not something which differs, the sigma bonds, but the pi bonds do. And therefore our correct answer is B. 1 and 3 differ, and the others do not. And then thinking about why the boiling point actually differs, what the reason for that is, it's a bit more complicated than you need to know for the MCAT, but it has to do in terms of polarity and van der Waals forces. So the main difference is that additional pi bond in the triple bonded one, and that pi bond is more polarizable. What happens in van der Waals forces is that we have some transient dipoles, meaning even though both the carbons have the same electronegativity, at some point some electrons are closer to one atom versus another, so we have a slight positive and negative charge on the respective carbons. And then if we have different molecules having this, they'll be attracted to each other's positive and negative charges. This is what causes van der Waals forces. And so if the pi bonds are more polarizable and the triple bond has more, then it has more van der Waals forces because of that. Also the triple bond is shorter, and so it's a shorter molecule, the ethyne, and it has the 2 carbons closer together. Van der Waals is also a function of the distance between different atoms, so shorter molecules in a solution, we have more of them together and seeing another atom that's nearby them, therefore we have more van der Waals forces. So just keep in mind that it's that extra pi bond which leads to more van der Waals forces and therefore more intermolecular attractions, right? Because we always say boiling point is dependent on intermolecular attractions. These both have the same number of carbons, so you would think that for the most part the van der Waals forces are the same, but no, that pi bond also plays a factor. Because of that, we have differences in boiling point. In question 103, it says the boiling point of methane is 110 Kelvin, while the boiling point of germane, which is GeH4, is 185 Kelvin. The difference in boiling points is primarily attributable to which of the following? So 110 Kelvin is the boiling point for methane, and then this is for germane. We have a difference in boiling points. What can we attribute it to? So we're comparing these two because methane, you should know, is CH4, and this one is a different central atom, but it's still H4. So why do we see this significant difference in boiling points? Well, boiling points largely have to do with intermolecular attraction, so not within a molecule, but within the interaction between different molecules. And one thing to keep in mind, something that might have caused you to choose the wrong answer, is that it doesn't really depend too much on polarity. Because keep in mind, let's write like this. I'm just trying to very quickly draw the stereochemistry. Just keep in mind methane is a tetrahedral molecule. So is germane, okay? Because these are tetrahedral, their polarity, even if there was any, it's going to be distributed evenly across the 3-dimensional plane, and therefore that polarity cancels out. So overall, we have a non-polar molecule. So if instead of like all hydrogens, if I had a chloride instead, sometimes it would be, it would have polarity, but if they were all chlorides, then that would all cancel out, and then it's a non-polar molecule. So let's look at the answer options now. In option A, it says the difference in electronegativity between the carbon and germanium is what leads to the difference in boiling points, and B is similar. It's talking about the difference in polarity in the bonds, and of course if there was more electronegativity, or if there was a difference in them, then there would be a difference in the polarity. And yes, this could be a possible reason. Like there is an electronegativity difference between carbon and germane, but as we said, because of the tetrahedral nature of the molecule, that polarity is not an important factor. So it's not because like one is more polar and the other isn't, and then we have these reactions occurring because of this dipole-dipole interaction, because of the polarity, and that's what leads to the change in boiling point. We're talking about the primary, what it's primarily attributable to, and there's something else which is a more important factor. Option C is saying the difference in size between carbon and germanium, and yes, that's it. Size is very closely related to van der Waals forces. So van der Waals is dependent on both size and then the distance that there is between different atoms. And of course, if you have more size, more surface area, you're interacting with more atoms and more molecules around you. Therefore, more van der Waals forces. And so the one that has a bigger size is going to have more van der Waals, more intermolecular attractions, and therefore a higher boiling point. And D is incorrect. It's talking about ionization energy, which is the energy required to ionize or remove an electron from the valence shell. Well, okay, there might be a difference in that, but that's not directly related to intermolecular forces and therefore not really related to boiling point. So we can remove that answer. In question 104, it says compare the molecule shown with a separate molecule in which the NO2 group moves to the adjacent carbon atom. The alcohol in the second molecule is then deprotonated. Its pKa would be expected to blank. So compare its pKa to this given molecule. So we have the molecule shown, and then we have a separate molecule, and the NO2 group moves to the adjacent, NO2 group moves to the adjacent carbon atom. Alcohol deprotonated, tell me about its pKa. So if we have this molecule, say this one got deprotonated, so we're talking about the pKa and the acidity of that OH group. If this got deprotonated, it could have some resonance going on, where instead of the oxygen just carrying that negative charge, we can have the oxygen move around the negative charge. So if it comes down, forms a double bond with this carbon over here has too many bonds now, it has 5, so it breaks a bond, the negative charge moves over. Let's draw another resonance form. Now it looks like this. And if we draw out NO2 properly, it looks like this. So it can also participate in resonance. And then here is how it participates. If this negative bond comes to, or if this negative charge comes here to form another bond, now this double bond has to move, and then nitrogen has too many bonds, so it has to break the bond with that oxygen that it had. So our molecule now looks like this. So essentially the charge is over here. It moved from that top oxygen down to one of the oxygens that nitrogen is connected to. The difference now, if we had the NO2 on an adjacent carbon, let's say we are at this step, there's a negative charge over here, it looks like this. Now NO2 is here, and this molecule is symmetric, so it doesn't really matter where I specifically move it. This carbon atom over here that NO2 is attached to has 4 bonds right now. If we try to move the negative charge down here, now the atom has too many, so it has to break one of its bonds. So it breaks the double bond, but the double bond can't come here because it's still bonded to that same carbon. That carbon would still have 5 bonds. So the only place for it to really move would be over here, and then there's too many bonds now, so this double bond has to move. Where can it go? It can't really go anywhere. If it goes here, then it has to push back to the oxygen, and then that oxygen, there's no real resonance going on because it still has that negative charge. You could also move it over here, put a negative charge over here, and so you see what's happening is there's a negative charge and it can kind of be moved around the ring, but there's less resonance than was available in the original molecule because we don't have the NO2 to participate in the resonance. So that's the main difference. there's less resonance stabilization when we move the NO2 over. And what you should know is when there's more resonance, that means that since that negative charge is not just held by one atom, because oxygen would not like to have that negative charge, if it can distribute it, then it's more satisfied, and therefore that conjugate base, the conjugate base that's formed after the proton is lost is more stable, and therefore the pK would be lower because oxygen is more acidic now and it's fine with losing its proton, so lower pKa means a stronger acid. Compare that to the second molecule that we're talking about. If we move the NO2 over, then we don't have as much stabilization, therefore this molecule is not as great an acid because the base is not as stable, so pKa goes up. So essentially what we derived from all of that is that pKa goes up. So that's what we're looking for. Option A is saying we see an increase in pKa because the modification allows for better resonance to stabilize the negative charge. No, there isn't better resonance, there's worse resonance. Option B is incorrect because it's saying there's a decrease in pKa and also better resonance part. Option C is saying there's an increase in pKa because the modification eliminates the resonance stabilization of the negative charge. Yes, it greatly reduces it. And then D is incorrect because it's talking about decreasing the pKa, but no, pKa goes up. In question 105, it says a researcher uses the molecule shown as an acid catalyst to enable a reaction between a carboxylic acid and an alcohol. The reaction is designed to occur in water. Due to the relative insolubilities of the two reactants, the acid catalyst can help. Which of the following best explains the catalyst's mechanism of action? So we're using this acid catalyst, which is shown right here. We have a reaction between a carboxylic acid and an alcohol. It occurs in water, but the molecules are insoluble. The two reactants that we're talking about a carboxylic acid and an alcohol. Usually when you think of these things, you think of them as being soluble in water, but in this case, an alcohol can just be any ROH, right? So if we have an ROH where the R is very long, like a lot of carbons, then we have something that's very nonpolar. So overall, it's not really soluble in water. Same thing goes for the carboxylic acid. So we have reactions that are not really soluble in water, but we're still trying to carry out the reaction in water. And an acid catalyst would definitely help this reaction take place. Some protons are needed. So which of the following best explains the catalyst's mechanism of action? So the main way in which it can help, first of all, we need protons to be present for this reaction to take place. Otherwise, if the carboxylic acid is negatively charged, if it's deprotonated, then it's not really going to react, because then you have a carboxylate, which is not reactive. So you want protons present. That's why we're trying to have it occur in water. An acid catalyst would help because it would have more protons be present. So the two main ways it can help is, one, the acid present helps us have a more acidic environment and the reaction is going faster, but we want something different because there's a reason that we use this specific catalyst, and it has to help us somehow, because we're told in the question that we have a reaction that's occurring in water, but the reactants are insoluble. So it would make more sense if we use it for a different reason, because otherwise we could have used this any acid, right? So it makes more sense that it helps them be more soluble. And so you can see here we have an amphipathic molecule. We have a very nonpolar side and then a polar side. The polar side can dissolve in water. The nonpolar side, it's going to aggregate. When we have something like this, with like one long chain, and it has both a polar and nonpolar side, what happens when we put it in an aqueous environment like water is it forms something called micelles, which look like this, where those circles represent, I should keep it consistent, the circles represent the blue part over here, that hydrophilic head. They come to form a circle and interact with the water that's on the outside, and they protect the rest, the nonpolar side, and keep that side from having to interact with the water. Therefore, on the interior, we have a hydrophobic environment, and then these insoluble reactants that we're talking about can come inside this environment and then take place in their reaction. And then we also have some protons present because we have an acidic environment, so the protons we need are there, and then the molecules are now much more soluble, and therefore the reaction can take place much faster. That's why we use this specific acid catalyst. So option A is saying, regarding the mechanism of action, it's saying the acid catalyst forms a micelle with its long chain hydrocarbons pointed outward. Because it says outward, this answer is incorrect. And the rest is fine. This allows the acid and alcohol to react in the presence of water. If the hydrocarbons were pointed outward, then there's no real environment for the reactants to be safe in and carry out the reaction in. B is the correct answer. Inward is where we have the long hydrocarbon chains pointed. And the key part here is the micelle. That's very important. That's a structure that they form, which is why we use this type of acid catalyst. Option C is saying the acid catalyst provides an attractive leaving group. First of all, no, it doesn't provide a leaving group. Second of all, the long chain hydrocarbons, that's definitely not a good leaving group. That would be a terrible leaving group. Option D is saying it provides many acidic protons along its chain hydrocarbon. No, the acidic protons are not on the chain hydrocarbon. Those are hard to remove. It's this one. That's the acidic proton. So D is incorrect, and it's also not talking about the micelles. So it's a completely incorrect answer. B is the correct answer here. That's it for the questions in this video. If you enjoyed what you saw, make sure to check out our course. The link is right here, as well as in the description below. And in that course, we go through a lot more questions just like this and explain all the different answer options so that you're prepared to have the right thinking for the MCAT. Other than that, make sure to subscribe here to this channel to stay up to date with the videos that we post here. That's it for this video.